Hello and welcome to this video on what is linear regression analysis. My name is Geiser, I'm an instructor with QuantFish. In this video I want to give you a basic introduction to linear regression analysis. So let's get started. First of all, conceptually, what is linear regression analysis about? Linear regression analysis allows us to make predictions of a single outcome variable, such as, for example, life expectancy, from a set of so-called predictor variables or explanatory variables that are used to predict this outcome variable. For example, life expectancy might depend on diet and nutrition, so that could be our first predictor variable, or x1. Exercise could be another factor that could explain differences in longevity, and so could be whether you smoke or not, genetic factors, and many other types of variables. And so linear regression analysis is used to find out what the most important determinants of an outcome variable are, what the relative weights are that these predictors carry in the prediction of the outcome variable. So in other words, what is the most important factor in, for example, longevity, and to also make predictions of future scores. So we can use a regression model to then estimate predicted scores based on a specific profile of independent variables. In linear regression analysis specifically, we assume that there are linear associations between the predictor variables x and the outcome variable y. And we assume that the outcome variable y is a continuous or metrical variable. If you have non-continuous variables, for example, if you have a binary variable such as life, death, or yes, no, then you would use what is called logistic regression analysis, which I do not cover in this specific video. So then the goal of linear regression analysis is to determine the weights of the different predictor variables. Those weights here are indicated as B1, B2, B3, and B4, and we will see later on how those are how those find their way in the analysis more formally. Also, in regression analysis, the predictor variables can be correlated, and in fact, a partial overlap of the independent variables is what makes regression analysis valuable, because it allows us to figure out and take into account those redundancies, so that we can see, for example, if another predictor adds something above and beyond what is already explained by a previous predictor. So for example, individuals who smoke maybe tend to not exercise as much, or maybe they tend to also not have the healthiest diet. So there might be some overlap here in the predictors, some partial redundancies, and regression analysis allows us to estimate the weights B1, B2, B3, and so on in light of that redundancy that is reflected in covariances or correlations between the independent variables. And therefore, regression allows us to uncover predictors that may be redundant and to say we don't need this predictor because what this predictor explained is already better explained by one of the other predictors. Also, regression analysis acknowledges that typically our prediction will not be perfect, because first of all, we have measurement error typically in our dependent variables, so life expectancy can maybe not be measured with perfect accuracy or reliability, so there's some random noise involved here that leads to prediction errors. And then also we typically do not have access to all of the predictor variables that are relevant. There might be factors that we might be missing or that we cannot measure, or there might be also nonlinear relationships or slightly nonlinear relationships that we fail to model appropriately that lead to prediction errors, or interactive effects between predictor variables maybe that we don't see. And so there's some error involved, and that's captured by an error variable E that is also part of the analysis. Now let's take a look at regression analysis more formally. So what does this look like in terms of a mathematical model? Linear regression is based on a single equation that you can see here. And so in this equation here, we have y, x, j, and e, which are variables. Y is our dependent variable that we also sometimes call an outcome variable or a criterion variable. So that's the variable that we want to predict, for example, life expectancy. The xj variables are our predictor variables that we also sometimes call independent variables or explanatory variables, because those are the variables that we use to predict our outcome variable. And then E is our error variable that captures unsystematic influences, meaning random measurement error in the outcome variable, as well as omitted causes of Y, omitted predictors, nonlinear relationships, and other types of things. And then the coefficients in this equation that are labeled as B are the intercept B0, so that's an additive constant. That is the expected value of the outcome variable when all predictor variables take on the value of 0. And I will talk about this in a little bit more later. And then the B1, B2, Bj, Bk coefficients are the regression slope coefficients that we also sometimes call partial regression coefficients, because they take into account the redundancy of the predictors if they are correlated. And so those indicate the weight of each predictor. So that would mean, for example, B1 would indicate the expected change in our outcome variable y for a 1 unit change in our predictor. And that interpretation will become clearer later on when I show you an example. So in summary, one of the goals of regression analysis is to estimate the regression coefficients B0 as well as Bj, so that we can come up with an equation that provides for the best possible linear prediction of our outcome variable from our set of predictor variables. But that's not the only goal of linear regression equation. Another goal is to determine the overall fit, meaning how good of a job does our regression model overall do with all the predictor variables in predicting the criterion. And there are some overall single number fit statistics that allow us to describe the overall fitness, so to say, of our model, or the overall performance of our regression model as a predictive model. And so the first two that I want to discuss here are the multiple correlation and the coefficient of determination. For that, let's revisit the regression equation for a second. So this is the same equation that I showed you previously, where we have k predictor variables. And so then with this equation here, we have the equation for our observed criterion variable y with an error term at the end. We can also write the regression equation for the predicted y-scores, and we call those y hat. So notice that in the second equation here, we have y hat instead of y, and we don't have an error term e at the end. This means that this is the equation that we can use to predict y-scores. And so the y-hat scores are different from the y-scores unless we have a perfect prediction. So this means we can look at y versus y-hat to find out how much discrepancy is there in our observed y-scores that we actually found in the data and the y-hat scores that we would come up with if we had only access to the predictor variable. So if we had to make a prediction based on the x variables, then what would the y variable look like? And so what we can do then is we can correlate the observed or actual y-scores with the predicted y-scores. So we can simply calculate the bivariate correlation or Pearson correlation between y and y hat, and that gives us the so-called multiple correlation R. So the multiple correlation R is nothing but the bivariate correlation between the observed y-scores and the predicted y-scores. And so the closer or the better our prediction based on the x variables, the closer y will be to y hat and the higher the correlation between y and y hat will be. In the ideal scenario, the multiple correlation will be 1.0, which will be the case if our predictors allow for a perfect prediction of the y scores. The worst case scenario would be that the x variables explain nothing. Then the multiple correlation would be 0. That would be really bad. That would mean our regression model really sucks, so to say. Now, based on the multiple correlation R, we can then directly calculate the coefficient of determination, which is simply R squared. R squared is so the squared multiple correlation, and that has a special type of interpretation that many people find useful. R squared can be interpreted in terms of the percentage or proportion of variance in the dependent variable y that is accounted for by the independent variable. So for example, if you find R squared is 0, then 0% of the variance in the dependent variable is explained. An R squared of 0.5 would mean 50% of the variance in the dependent variable is accounted for by the independent variables x. So that can be used as a measure of effect size for the overall regression model. Now, there's a third measure of overall fit in regression that is useful, and that's called the standard error of the estimate. The standard error of the estimate is the standard deviation of the error scores E. So remember that E is the error variable, and E is the difference between y and y hat. So as a result, we can calculate the error scores for each person, EI, by taking the difference between a person's observed y-score and that same person's predicted y-hat score. So here in this formula, you can see that we're doing this for all individuals, for all n people in our sample. So we're taking the difference between y and y hat for each person. And then we're squaring those differences, which is the same thing as taking the sum of the squared error scores across all n individuals in our population or sample. And then we divide by n minus k minus 1, where k is the number of independent or predictor variables, and we take the square root. And then that gives us the standard deviation of the error scores, which has a nice intuitive interpretation as the average prediction error. So you could say this is, so to say, the average amount by which we are off with our prediction of our x score, of our y scores from the set of predicted scores. And we'll see later the interpretation in the example. This will become a little bit clearer. Also in regression analysis, we have inferential statistics. So we also conduct tests of significance typically to find out whether a given effect is statistically significant. And the first test that we usually conduct is an omnibus F test. The omnibus F test tests whether the squared multiple correlation is significant in the population. So here you can see that the null hypothesis is rho squared equals 0. Rho is the Greek letter that is used to indicate the multiple correlation in the population. And so rho squared then is the coefficient of determination in the population. And the null hypothesis is that that squared multiple correlation is 0 in the population. The alternative hypothesis is that rho squared is greater than 0, and this can be tested with an F statistic that has k numerator and n minus k minus 1 denominator, degrees of freedom, and it's calculated according to the formula that you can see here, where you can see it's a direct function of R squared as well as the sample size and the number of predictor variables. So then we can take a look at whether the F statistic is significant. We can determine a p-value for the F statistic to find out whether our coefficient of determination R squared is significantly different from 0. Next are T statistics that are conducted after we find a significant F statistic to find out whether individual predictor variables xj are significant predictors of our dependent variable. So this is kind of similar to what you would do in an analysis of variance for comparing the means of j different groups, let's say, where you would first conduct an omnibus F statistic, and then after the omnibus F statistic is significant, you would want to find out which of the groups differ significantly in their means. And so here we're doing the same thing. We want to find out which of the k predictor variables are statistically significant after a significant omnibus F statistic. The t statistic then tests the null hypothesis that the regression slope coefficient or partial regression coefficient beta j in the population for a predictor xj is 0 or not. And so this can be formulated either as an unspecific hypothesis, where you can see the alternative hypothesis here is simply that beta j is not 0, meaning that in the population there is some sort of effect, but we don't know whether it's positive or negative, because beta could be positive or negative depending on whether the predictor has a positive or negative association with the dependent variable. Or the hypotheses can be formulated as specific hypotheses. Here the specific alternative hypothesis could be that beta j is positive, meaning greater than 0, if the predictor is hypothesized to have a positive association with the dependent variable. And so depending on that, the t statistic can be used as a two-tailed or as a one-tailed test. A two-tailed test would be used for an unspecific hypothesis, and a one-tailed test could be used if the a priori hypothesis was specific, like it is in the example on the right-hand side here. How is the t statistic calculated? The t statistic is calculated by dividing the sample partial regression coefficient bj by its standard error se bj. And the t statistic has n minus k minus 1 degrees of freedom, and then we can look it up in a t-table, or we can use a t-distribution calculator to find the p-value. As we will see, programs for multiple regression analysis such as SPSS directly provide us with a p-value for the t-statistic. So let's take a look at a concrete data example with two predictor variables. In this example, my dependent variable is salary, and the predictors that I'm using here are age and IQ score. And this example is not based on actual data, but rather on simulated data to make it more easily understandable. And so in this example, we have two predictors, they can be correlated, and so we're estimating two partial regression coefficients, B1 and B2, as well as an intercept and our coefficients of fit. So let's take a look at what the results for a multiple regression like that look like in the SPSS software. In the first part of the SPSS output, you obtain a model summary table that contains the multiple correlation R, the squared multiple correlation or coefficient of determination R squared, an adjusted R squared value, as well as the standard error of the estimate. The multiple correlation R here is very high, 0.906, which is much higher than you would typically see in practical applications. The R squared then is 0.822, which indicates that 82.2% of the variance in salary is accounted for by age and IQ score combined. Now, the sample R squared tends to overestimate the explained variance in the population, and therefore an adjusted R squared is also provided by SPSS. The adjusted R squared or shrunken R squared provides for a more realistic estimate of the explained variance. You can see it is smaller here, 0.771, so more realistically, more conservatively, so to say, we can assume that about 77% of the salary variability is explained by age differences and differences in IQ scores. The standard error of the estimate here is 7,346 or 7,347 if we round it. And so this standard error of the estimate is in the metric of the dependent variable, meaning in salary dollars. So this means that our prediction of salary from age and IQ score is typically about $7,347 off, plus minus. So we over or underestimate the salary on average by about $7,347, which is relatively high, even though our R squared is fairly large. So this puts the goodness of fit in a different perspective, because it allows us to look at that in terms of the average prediction error in the metric of our dependent variable. The next table in SPSS provides the results of the omnibus F statistic that is used to test whether R squared is significantly different from 0. And you can see here that this looks very much like an analysis of variance table that you would obtain for a design where you test for mean differences across different groups. However, here the sum of squares refer to the regression and the error. And then you also get degrees of freedom and mean squares, as well as an F statistic and a p-value in the last column. You can see here the F statistic has 2 numerator degrees of freedom. That's the number of predictors is 2. And it has 7 denominator degrees of freedom, which is n minus k minus 1. So here the sample size is 10 and we have 2 predictors, and then minus 1 is 7. So F with 2 numerator and 7 denominator degrees of freedom is 16.121. And that is statistically significant at the 0.05 level with a p-value of 0.002. So this means the null hypothesis that rho squared is 0, that the multiple correlation squared in the population is 0, can be rejected at the 0.05 level. This is a significant regression model, so to say. Overall, we find a significant R squared value. Now, after that, we typically also want to find out which of the predictor variables contributes to this significant R squared value, and we find that out in the next table, where we get our regression coefficients as well as their standard errors, t-statistics, and p-values. In the first column here that SPSS labels unstandardized coefficients B, we obtain first of all our intercept B0, which here is negative 94,836.976. So that's the intercept, and that would indicate that for individuals who have an IQ score of 0 and 0 years of age, we would expect that they make negative $94,837. So that doesn't really make a lot of sense, because we don't have anybody with an IQ score of 0, and it also wouldn't make any sense. And we definitely don't have anybody who is 0 years of age. And that also doesn't make sense to measure salary for individuals who are newborns. So therefore, the intercept here is meaningless, because our predictor variables don't have a meaningful 0 point. Now, the intercept would be meaningful potentially if we had meaningful 0 points, like for example, if your predictors are, or one predictor is the number of siblings in that you have, then 0 could be meaningful. If you have 0 brothers and sisters, then that could make sense. Or if you centered your predictor variables. So if we had centered IQ scores at the mean, and if we had centered age scores at the age mean, then also the intercept here would be meaningfully interpretable. But if you have predictors that are not centered and or that don't have an otherwise meaningful 0 point, then the intercept is not really interpretable. What is interpretable here are the partial regression coefficients B1 and B2. B1 here is 1,195, and that indicates that for every 1 unit increase in IQ scores, we expect a salary increase of about $1,195. So there's a positive relationship there between IQ scores and salary. Also, age in years has a positive relationship with a B2 coefficient of 696, which means that for every additional year of age, we expect a salary increase by $696. Next is the standard error for these coefficients. And that standard error then is used to calculate the t-statistic, which you can find in the second to last column. Here, the t-statistic for IQ score is 5.262 and has a p-value of 0.001, meaning that IQ score is a significant predictor at the 0.05 level. Also, age in years has a significant partial regression coefficient with a t-score of 3.14 and a p-value of 0.016. So both predictors in this case have a significant contribution for the prediction of salary dollars. In addition to that, we also get standardized regression coefficients that SPSS calls beta. There's no intercept in a standardized regression because when the variables are standardized, their means are 0 and then the intercept also is 0, but the B1 and B2 coefficients are provided. And so now these are interpreted in standard deviation units, meaning that for a 1 standard deviation unit increase in IQ scores, we expect a 0.857 standard deviation unit increase in salary dollars. Now that's not as easily interpreted in this case as are the unstandardized coefficients, because the standard deviation units here with regard to salary are not as intuitive as are the dollar units. So in this case, I would say probably the unstandardized coefficients are easier to interpret than the standardized coefficients. But in other cases, when you have arbitrary metrics of your independent variables, then it may be easier to interpret the standardized coefficients. And also the standardized coefficients allow you to compare the relative influence of the different predictor variables. So in certain cases, the standardized coefficients may be preferred over the unstandardized coefficients, but in many cases, you would want to use the unstandardized regression coefficients for the interpretation. Now, the regression analysis also comes with a number of assumptions that I want to mention here, because it's important to make sure that these aren't violated, because that might compromise your outcomes and your tests of significance of your regression analysis. The first assumption is that your observations are independent, and that is typically met when you have a simple random sample from the population. Then there should be no dependencies in your data, but it can be violated when you have clustered data. So meaning, for example, individuals nested within companies or students nested within school classes. If you have such cluster sampling, then individuals who are in the same group may be more similar to one another, and there might be correlated observations, and that can be a problem for tests of statistical significance. That can increase your type 1 error rate. It can lead to type 1 error inflation. And so you want to avoid that if you can. If you have clustered data, then you can use multi-level modeling, multi-level regression analysis, which allows you to address this issue appropriately. Also, the dependent variable should have interval scale level. If you have dependent variables that are only binary or ordinal, then you can use other types of regression analysis, such as binary logistic regression analysis, multinomial logistic regression analysis for polydomous nominal dependent variables, and there's also ordinal regression analysis for ordinal outcome variables. Furthermore, the linear regression equation implies that we're assuming a linear relationship between the x variables and the dependent variable. If you have nonlinear relationships, then you want to address those appropriately, and I will say something about that also in a little bit. Furthermore, as in analysis of variance, we make the assumption of a normal distribution of the error scores. So you want to check that the errors E are normally distributed, for example, by taking a look at a histogram of the residuals, which you can obtain, for example, in SPSS, or a normal probability plot of the residuals, which allows you to figure out whether the residuals are approximately normally distributed. Also, we make the assumption of homoscedasticity of the errors, meaning equal spread or equal variance of the error scores E for different values of the dependent variable Y. And you can again check that best by using graphical displays, so a plot of the residuals against the dependent variable, which you can also obtain, for example, in SPSS. And then finally, an assumption that is actually maybe most difficult to meet is the assumption that the independent variables or predictor variables xj have no measurement error, or that they're measured with perfect reliability. This is something that can be very difficult to meet in practice, and it can lead to bias in the regression coefficients and the tests of significance if this assumption is violated. I'll say something about what you can do in that case also on the next slide. So here, finally, then the final thing that I want to talk about is extensions of the standard linear regression model. So we can also include interaction terms as in an analysis of variance. So we can have what's called moderated regression, where we have product terms between X variables that allow us to model potential interactive effects between the predictors. That can also be done, and we can have nonlinear terms in the regression. If you have, for example, a U-shaped or inverted U-shaped relationship between a predictor and the outcome variable, you can include an x-squared term in your regression model to model such nonlinear relationships. And there are also other terms that you could include, such as x-cubed, for example. Furthermore, there is multivariate regression, which allows you to look at more than one dependent variable at a time. And there's path analysis, which allows both for multiple dependent variables and also for multiple mediator variables, meaning variables that are at the same time independent variables and dependent variables. So you can look at complex causal chains of relationships between variables using path analysis, which is a generalized, more multivariate regression model. And then finally, we have structural equation modeling, which allows us to do what we can do in path analysis, meaning we can have multiple independent variables or predictor variables, multiple mediator variables, and multiple outcome variables in a single model. And we can also have latent variables that are measured with multiple indicators. And that allows us to address the measurement error problem in the independent variables that can jeopardize our linear regression results. In structural equation modeling, we can take into account random measurement error or unreliability in all variables by using multiple indicators. And if you're more interested in that, check out the description for workshops that I teach for QuantFish, where I discuss models like this: path analysis, structural equation modeling, and factor analysis. I hope you found this video useful to learn about linear regression analysis. If you did, please subscribe to this channel, and I'll see you in the next video.